Okay, well, welcome to our program on nuclear energy in Nebraska. Quick facts. My name is Peggy Apthorpe, and I am currently working as an AmeriCorps with Conservation Nebraska's Common Ground program. Conservation Nebraska, as many of you may know, is a statewide nonprofit that is dedicated to keeping our natural resources healthy. We do that in a number of ways with programs and events like the one that we are hosting this evening. If you would like to learn more about Conservation Nebraska, you can check out our website at neconserve.org or follow us on Facebook. And that's a good way to keep updated on all the various programs that we have going on. Before I introduce our speaker, I would like to cover a few housekeeping items. You will be muted and your camera is off. We would encourage you to put questions or comments in the Q&A or the chat, and then we will address those at the end of the program. And there will be a survey that pops up at the end of the program. We would really appreciate it if you could take the time to complete that, as it helps us with planning and funding types of issues. It's really my pleasure to introduce our speaker, Dan Buman. Dan is an expert in the area of nuclear energy. He is the Director of Nuclear Oversight and Strategic Asset Management for Nebraska Public Power District, where he has worked for 35 years, I believe. You can correct me if I'm wrong there, Dan, but and he has a degree in electrical engineering from the University of Nebraska and an executive master of business degree from UNO. He is a Nebraska native, and again, he's an expert on nuclear energy in our state. So we're really happy that you could take the time to spend with us and help us learn more about this, Stan. We really appreciate that. I'll turn the program over to you.
Okay, thank you very much, Peggy. I really am excited, and I really appreciate having the opportunity to be able to talk about one of my most favorite subjects here. We're going to talk about nuclear energy in Nebraska, and we're going to kind of go, give you kind of I don't know what all of your backgrounds are, so I'm going to start off at the beginning, just kind of giving kind of a background of how nuclear power works, talk a little bit about the fuel storage, transportation. We'll talk about how the role nuclear power serves in the broader system of electrical generation and some of the benefits of nuclear power, and how does nuclear fit into decarbonization, and then nuclear energy in Nebraska now and also in the future. So what you're looking at here at the very beginning is a picture of Cooper Nuclear Station. Cooper Nuclear Station is currently the only active nuclear plant in the state. We produce about 800 megawatts of power. That's enough for about 350,000 homes on average, and it runs 24/7. So we're situated in south of Brownville, Nebraska, on the Missouri River, and we'll kind of talk about that as we start going forward. So when we look at how nuclear power works, we basically, instead of having gas or coal or anything else, what we do is we actually use uranium. And we have uranium. There are actually two types of uranium. In nature, you see a lot of uranium-238, and that's just the number of, it has a number of protons and neutrons in the nucleus, and a total of 238 of them. There is a smaller portion of that which we use inside the core of less than 5% of the fuel that we put in there is what we call uranium-235. And uranium-235 has a characteristic that if a neutron were to strike it at the right energy, it will go in and it will excite the nucleus, and it will split apart, and it'll come into two smaller little elements. And then also produce between 2 and 3 neutrons that will come on out to be able to carry the chain reaction and keep it going. When that occurs, there's an awful lot of energy that comes off. That comes off mostly as heat. So if you look here, what you see is a kind of a diagram of, start over here on the left-hand side. The heat inside the vessel's full of water. So that heat starts heating up the water. That water turns into steam. That steam goes over, it turns a turbine. turbine comes on down and turns the generator, which produces electricity that goes out to the homes. All the steam coming from the turbine then comes down through a condenser, and we actually at Cooper Nuclear Station, we use Missouri River water that is pumped through. The condenser's at a lower vacuum, so if any sort of leaks, the river would leak in. There would be no way that you'd have anything that would leak out, but it cools basically that steam back to water where it's pumped, and it's pumped back to the vessel. And you see surrounding all of the vessel is a containment structure that basically is designed to be able to withhold all the energy that's inside the vessel and be able to disperse that, and so that it contains all the radiation. Now, this is the simplest way that it goes, because we heat the water directly and it boils. But there is other designs, and the other current designs that are out there are something that's called a pressurized water reactor. And in that particular one, what you do is, once again, over on the left-hand side, you basically have heat going in, but the water is kept under such pressure that it never boils. And so that goes over to another heat exchanger or a steam generator there, where the steam is going, and then that just cycles back. So it's basically an isolated loop. When you start hearing about some of the advanced nuclear reactors and some of the other things that are coming in, you'll hear terms like, sodium cooled reactors and, molten salt reactors. All of those are talking about what they use to basically cool, to transfer the heat out of the core. And all of that is done in a step fashion very similar to this. So those are the two general times, but in both cases, we use that heat to basically produce steam to be able to turn a turbine. When you get out to the turbine and to the generator, that's really no different than anything that you'd see at a normal gas plant or at a coal plant. All of those it's the same technology at that particular point. So nuclear fuel is made up of a series of fuel pellets that we have that's inside the core. And each fuel pellet is roughly about the size of a pencil eraser. There is what you see. So it's a very concentrated energy form. So again, we use about 10% of the total energy out of it. But what we will do is we would have in that little pencil shaped fuel pellet, it has about the same amount of energy, as you can see there, as 17,000 cubic feet of natural gas, roughly a ton of coal, or about 149 gallons of oil. So when you look at the coal train over there, when you take one of those box cars over there, that's basically, when you do the math and going through that, that's roughly the same as 120 fuel pellets. So these pellets all fit inside of a fuel pin. And here's what you're looking at, a series of 4 fuel bundles. And you can see the little rods that are over there on the right-hand side. Those pellets are stacked in there, one on top of each other. And so they're in a sealed tube. It's filled full of helium so that it's inerted. It's seal welded in, and all of the fission products all stay within that. And what happens is that heat comes out, water comes up around the tubes, but the tubes protect that, and it's always a barrier between that and the water. So you have 92 of those fuel rods in each bundle. We have 548 fuel bundles. If you go through and do the math, you have almost roughly 19 million fuel pellets that are inside the core. We will run for a 2-year period. We will shut down and we'll refuel. When we take a fuel bundle in, they run for six years. So every 2 years, we will shut down. We'll replace roughly about a third of the core, about 180 bundles out of the core. So when you put that all back together and put that in there and look at the math, I've got a little, just kind of a trivial question. So all that energy is put in there at the time of when we start up from a refuel. Once we start up, we're going to be running for 2 years and basically run 100% power the entire time frame. So at that particular point, when you look at all the energy that's inside the core, so following a refueling outage at CNS, if you were trying to take how long of a coal train would it take to transport equivalent amount of energy, you have a guess of how long that coal train needs to be. So When you sit there and look at it and you do the math, it comes out to be 1,400 miles, about the distance from here to New York City. So that's the equivalent amount of fuel that we put in every single fuel outage that's in there. The reason why that becomes so important is because when you get into things like Winter Storm Uri, when you get into some of these other extreme weather events, we have all the fuel on site. We don't have to worry about being disruptions and not being able to get the fuel in there, because we'll be continuing to operate for that. So when you look at the actual fuel bundles and you get new fuel on into the plant, what you're looking at here over on the right-hand side, those are two reactor engineers that are inspecting all of the fuel bundles as they come in. And you'll notice that how close they are to them, and you'll notice they're wearing the white gloves. The white gloves are not to protect them from the fuel, it's to protect the fuel from them. We don't want to get any sort of oils or any sort of material or anything else on there. So the cleanliness becomes very, very important to us. So what they're doing is they're inspecting all the fuel, each fuel bundle. They would put basically a channel around it, and then they'll put it down into the spent fuel pool, and it will go on in there, wait until we're ready to go for the next refueling outage. We'll be going into a refueling outage this October. We'll be shutting on down, and we'll be down for about a period of roughly about 30 days. And during that time frame, like I said, we'll be replacing about 180 fuel bundles. We'll be doing a whole bunch of inspections to make sure that we're not seeing any sort of wear on anything that's unexpected, doing maintenance, and any sort of upgrades that we'd be wanting to do. Once those go in there, like I said, they go into the spent fuel pool, and then during the outage, what you're looking here is the top of our reactor vessel. That's the reactor vessel head. So you can see the studs, they're actually loosening those up. When they get those off and get those big nuts off of there, they'll come down and they'll pick that whole thing up. And it looks like it's kind of in a stainless steel can. What will happen then is they'll basically flood all that all the way on up, and it will come on up to the very, very top. So when you're done, this is exactly what it looks like. And you can kind of see in the circle there, there's you can see it's filled full of water. It's flooded all the way up to the top. What you're looking now is you're looking down through roughly about 60 feet of water. So very high purity water that's in there. Right in the very center of this picture, you can see that there's it's kind of a long rod that's going on down. That's basically a telescoping rod that goes down. It's a robotic arm that goes down and grabs a hold of a fuel bundle, grabs it, makes sure that they have the right bundle. They're taking it up, they would take it out, and then to get over to the spent fuel pool, because they've now got this all flooded all the way over, they would basically come to the very bottom there. You see what looks like a little chute. They're able to take that and put that over into the spent fuel pool where it's kept and where it's cooled over there. So once it goes into the core or goes into the water, it basically will spend its rest of its life in there until after it's been discharged into the spent fuel pool. We allow it time to cool, and then we would basically put it into a dry storage canister that I'll go through and I'll talk about. As long as we have roughly about 10 foot of water and so the refuel rod is always underwater during this entire time frame. All this manipulation all happens underwater, and as I said, in some cases they're down about 60 feet. The little other circular thing that you see there is basically an inspection platform. You can see different technicians that are in there. They're doing various different ultrasonic and indications, and looking at making sure that they're not seeing anything that examinations make sure everything is in tip-top shape. Once it gets over into the spent fuel pool, we have fuel storage, and you see the top two items that are currently being used. So inside the plant, we have a spent fuel pool, and the picture over there is basically a fuel bundle that's in one of the spent fuel pools. So it's basically like a big swimming pool that's constantly filled full of water. It goes over there, it goes into storage, into that egg crate that sits down in there. Basically, and keeps it safe, makes sure that reactions don't start. It's cooled and shielded under, like I said, roughly about 20 feet of water when it's sitting on down in there. Typically that water is maintained around about 90 degrees or so, which gives plenty of time to be able to go in there, but it's an active components that we have, and we have pumps that are constantly running to be able to keep that cool. After that's been in the pool for a while, so we talked about a fuel bundle. We put a new bundle on in. It stays in the core for roughly 6 years. It comes on out. It sits over into the spent fuel pool. It'll sit there for probably about at least 5 years, between 5 and 10 years. And then what we will eventually do is we'll take that away and we'll put it into what's called a dry cask storage system. I'll show you some pictures of that. Those are the current storage facilities that we currently use. What's currently being looked at, and the government is still working on this, is looking at some consolidated facilities, some interim storage that would allow more efficient management. Right now, we store all of the fuel that we have right there on site. So we have everything. We know where every single piece of uranium, it's protected down there. There is a possibility, and one of the line items talks about we could extract more energy. We only use about 10% of the available energy out of it when we're done. Europe has, for some time frame since the 70s, they've actually recycled their fuel. They've been able to regain that out, and so you're able to, like, for example, for every 8 bundles you take out, you get a new fuel bundle that's coming on out of there. So again, there's some consolidation. It's currently being looked at again in the United States. That was originally President Carter signed the order and said that we weren't going to do that. There was fears of nuclear proliferation. That has not occurred. France has been able to show that they've been able to do that, and it's currently being looked at by the Department of Energy at this particular time frame as a potential be able to recycle that and again reduce down. People think of it as nuclear waste, but it really isn't waste. It's really used fuel at this particular point. Ultimately, where you would end up doing, they'd be looking at some sort of place of a permanent disposal in a deep geological repository. You might have heard of Yucca Mountain. That was where that was originally slated to go. They're not doing that. They're currently looking for another one. They're trying to work with local governments as far as looking to see, there's a possibility to be able to do that in a variety of different places. But again, they look and they will do a lot of analysis for the stability of the ground and making sure that it's all in there. So right now there is not a permanent location that they're doing. You are starting to see some of this in some of the other countries around the world. Sweden is having one where they're looking at it, where they're putting them down, and they're going down into the ground extremely deep, way below any sort of water levels or anything else. So there is no concern of contamination of the drinking water or anything else like that. So when we take that out of the spent fuel pool, we put them into something that's called dry cask storage. So what you see over on the left-hand side there, you see kind of a one canister. It has a bunch of different bundles in there. That's a vertical canister, or they have some of them that are horizontal canisters, like the picture right next to it, but it gives you some sort of idea of how big those canisters are. And the picture down below is basically shows you where the fuel bundles go in. So all of the fuel that's in there is all solid ceramic fuel. So it has not come out. It's not liquid or anything else. It's got water. So what we do is we put them in there. We will take that on out. We'll drain that out of water. We'll fill this whole canister full of helium, and it'll be a heat transfer, and it'll be able to go out. And I'll show you out on the pad when we move it out and we put it out onto the fuel pad. It just sits there, and it's just natural convection will keep it cool. So needs no forced pumps or anything else, no electricity. It just sits there. It's kind of like it has a chimney, so it has holes in the bottom where cold air comes in, it heats up, the hot air goes out through the top, and that natural convection will always keep it within about 2 to 3 degrees of ambient temperature. So again, it's an inert atmosphere that's in there. You can see it's very, very thick, and no driving, absence of no moving parts, no driving force is required for this. It's just all done very passive. So this is actually a picture of one of those casks. And so what you're seeing over on the left-hand side is one of the casks, and it's being removed up and out of the out of the fuel pool. That is the spent fuel pool there. It's like I said, it's about it's like a big swimming pool that's down there, very clear water. We put a canister, we put it down into the bottom of the spent fuel pool. They take and they move roughly about 168 fuel bundles that are in there. They select the ones, making sure that they've cooled down enough, and they put them into there. They will take and pull that up and out, and they'll put a lid on it, and it'll be robotically weld down. Once it's welded, they will basically drain it, purge all of it out, and they'll put in and fill it full of helium. And from there, they'll basically lower it on down onto basically a heavy hauler that you see over on the right-hand side, and it gets installed into a concrete storage facility that you're seeing over there. If you look right next to the gentleman's with a white hard hat, his head, you'll see kind of a little opening, and that's basically the opening where air is allowed to come in. It's heated, the air in there is heated, and then you can see up at the very top, there's little chimneys that kind of pop in and then are out of there. We monitor that 24 hours a day, 365 days a year, always looking and watching, make sure we don't see any sort of temperatures. As long as there isn't any debris or anything else, it like I said, it remains within about 3 degrees of ambient conditions. And then when you sit there and look at it, you can see this is the facility. So this is where all behind those white squares is basically one of those canisters that's in there. And this is the fuel pad for all the fuel that's been used except what's in the spent fuel for Cooper Nuclear Station. So a lot of people sit there and think about nuclear, and they're worried about nuclear waste, and I've kind of talked about potential for um, for recycling and everything. But when you look at that and you look at the size of that, if you took all of the fuel that's been burned in the United States since the mid 40s for all commercial plants and took it all and we're able to put it all onto a football field, it would basically fill the football field only 10 feet high. So it's very compact, so it's not like it's a large amount. So it isn't really a huge concern from waste. We are working our way through. It's stored very, very safe. You may wonder, it's sitting here. It's protected, as you can see from the fence. We have security officers, security manning this to be able to protect anybody from trying to come in and do any sort of damage to it. All of that is being done. It's being maintained very, very safe. May think about it sitting down on Missouri River Valley, and it's like, well, what happens about flooding? There's always flooding. Well, this is in an area that has never flooded. It's but well above the floodplain. But even if it did flood, they can operate under 20 feet of water. In fact, this same design was actually over in Fukushima when they had the tsunami that came in. They stayed put. It was unaffected by the tsunami, so the water came in, and then when the water came back on out, they've gone in, they've done examinations, there's been no sort of damage to them. So again, it's a very hardy and very robust design capable of doing that. Sooner or later, though, we would take that and we would be moving that to some sort of either interim or permanent repository. So the question always comes up about transportation. So those canisters would individually go into this is courtesy of NEI, but they would go into a canister like what you're seeing over on the right-hand side. They can go on rail by that, and going forward, these canisters, we've been doing fuel shipments from across the United States for 50 years. There's never been a release of radioactive material. They are very, very safe. If you ever want to see these canisters are tested for, they run locomotives into them. They'll take missiles into them. In fact, if you want to, you can Google Holtec missile test, and you can actually see some of what they try to put these canisters through, just to make sure that under the worst case event that they would not have anything. They would not have any sort of release of radioactive material. These canisters are very robust. In fact, for every ton of used fuel that you put in there, the transport casks typically have about 7 tons of material for protective containment, radiation shielding, and impact absorption. So they're very, very stout and capable. So we're going to go forward now, and we're going to look at electrical nuclear power and the broader electrical system and how that goes in there. But before I do that, just kind of wanted to point out this picture that you're seeing over on the right hand side that you'll see on these. That is once again a picture looking down into our core during a refueling outage. You're looking through 60 feet of water. So again, you can see the clarity that's in there. You see the down at the very bottom, the silver looking items, that little ring that's down there. That's basically new fuel that's been put on in. We talked about how we put in roughly about 180 bundles, so we're putting that in there. You see the little rod that's going down a little bit to the left of the center, and at the very bottom of it, you can actually see. I don't know if it's coming up on your screens or how well it's coming on your screens, but there is a fuel bundle that's down there at the very end. So they're actually moving one out and able to move through there. So again, the water clarity and the vision that they have is tremendous. The little black squares down there are places where they've taken fuel bundles out, and they'll be shuffling that around to be able to get the fuel into the right spot, just kind of like what you do with a campfire. You know, you move the coals around. That's the same thing we do. We keep the fuel bundles in for a total of 6 years, but after it's in the first time, they'll get them moved around to be able to make sure they get a nice even burn on there. So as I said, you know, every 2 years we shut down, we do the refueling outage, and we start up. So when you look at the system, it starts off here at the top at generation, whether it's hydro, wind, or some sort of generation unit. They basically transmit the electricity, generate the electricity between 2,000 and 24,000 volts. We step that up through a transmission system and goes off at 115,000 to 345,000. It's sent off then and kind of distributed out and starts going into sub-transmission. So we lower the voltage on down a little bit more. Then it gets into the distribution, like into the cities, and it's dropped on down. And eventually it'll get on down to where it comes into your house. And it comes in then at 120 volts, 240, or 480 volts. So from Nebraska Public Power, we have generation facilities across the state, and we have a very diverse generation portfolio. We believe that's very, very important to be able to provide reliable, resilient, economical energy that's always there. So we actually have coal, nuclear, gas, oil, wind, hydro, and solar across the state. And there you can see the locations of those. And you see down in the lower right-hand corner is Cooper Nuclear Station. Some of them we own the facility. Some of them we have purchase power agreements with them, like on a lot of the wind. Private developer has built those. We pay and we buy all the electricity from them, and they sell to us, and we use that and distribute that. Or in some cases, we have some of our retail towns that we have actually are putting up their own solar plants, solar facilities, like start off out in Scotts Bluff, York, Kearney, where they're able to produce some of that to be able to sell that, and we take that the excess energy with that also. So one of the reasons why we need such a diverse portfolio is all of these, there is no one perfect source of energy. All of these have their pluses, all of them have their minuses. And to give you some sort of idea, if we were to look at the last 3 years of actual generation by wind and actual load, now these are not to scale, but if you look at the top one, you can see it from 2021, 2022, and 2023. Those are the curves of the blue lines are what the loads really are. We have to produce electricity at the exact same time frame that it's being used. There is no, we don't have storage. We're starting to invest into batteries and other things to be able to have some storage, but again, it's extremely limited. So it's always, when you flip a light switch on, we need to make sure that you have the power there to be able to do that. So what you're looking at there in the green is when the wind energy is. Obviously, if the wind's not blowing, you don't get as much energy. So what I point out here is that you'll notice where the peak loads are, where the blue line is at the highest. That's typically where the green lines are the lowest. And you'll also notice where the blue lines are the lowest, the green lines are the highest. So what happens during those time frames is, again, you know, we don't have any way of storing it. So we will actually put into the market, it'll actually go into negative energy during those time frames, trying to reduce the amount of generation that's out there. and so it affects the overall market and the overall price that's in there. But again, you just see the correlation. It doesn't mean that wind is bad. There's a lot of value in wind, but it has its limitations. So you need something to be able to either flexibly power up or come on down, and be able to match whenever you need that to match the exact amount of load that you have with the exact amount of generation. Nuclear is one of those diverse energy sources. We typically are run and they have the highest average capacity factor. In other words, they basically run, they come on when they're on a 2-year cycle, they'll start up and they'll basically run at 100% power. Every quarter they'll kind of cycle down a little bit, just to do some testing and other things, but otherwise they're pretty much at 100% power the entire time frame. Cooper is operated for more than 697 days in a row. We've done that during the flood. We were able to continue to safely operate through that, through the extreme cold weather events in 2021. And again, you can see there we provide enough energy for 385,000 homes at their peak, operating 24/7, 24 months nonstop. So when we look at all that and we put all this diverse generation, all the coal, the oil, the hydro, the wind, the nuclear, what do we end up seeing? Well, we end up, you can see over there on the left-hand side, NPPD, we measure our actual carbon emissions, and for Nebraska customers in 2021 and 2022, a rolling 2-year average was more than 50%, 56% carbon free. That's been up as high as 60%. It varies as we're going around, but we constantly measure. The reason we do a 2-year average is we said every 2 years we basically shut down Cooper for about a month, and it has a big impact. So rather than reporting 90% one year and 40 down in the other, or whatever the numbers would end up being, we just do it on a rolling average that's in there. You can see that by far one of the biggest sources that we have of energy for our Nebraska customers is nuclear at 42.3%. So nuclear has a higher fixed cost, but it has a very low variable cost. But by mixing that together with the other sources that we have, we're actually been able to, EIA ranks Nebraska as the 5th lowest state for retail rates. And you can see the overall rates that we've had for retail, and you can see that they've been basically on a lowering trend since 2018. So there's a lot of discussion about decarbonization and how does nuclear fit into it? Well, nuclear has no emissions, so there is no carbon. So we basically are a firm load. NEI had actually conducted studies and went out, and you can see this is quoted from a study that they were looking at. And what our consultants have told us also is that as you're looking at reducing your carbon emissions, you can reduce about 90% of it, and it with some added costs, but getting that last 10% is what's really, really, really very, very difficult, and really starts driving up the cost. And so what you're seeing here is on the very bottom, you're seeing 2 different graphs there that says northern system, and what you see on the vertical axis is the average cost of electricity. And they use this study at different points, and they have 2 different scenarios here. The first one was in the system where there was no firm low carbon load. And you can see that as they started bringing the emissions down, going from 200 and trying to drive it down to 0, you can see what it did to the price of electricity going up very, very rapidly. Over on the right-hand side of that graph, you can see that they've added in now some sort of firm low carbon source, something like a nuclear power plant, something like that's able to generate with no emissions. And now you can see that driving it down to 0 is a much lower proposition. This study that was done actually came out with a couple of different highlights that they had. And again, it's talking about firm low carbon resources consistently lower decarbonized electricity system costs. And basically it's reducing the cost by 10 to 62% in 0 CO2 cases. If you don't have that, electricity costs rise rapidly as CO2 limits near zero. And it also looked at the ability of being able to use batteries or demand flexibility, which is other ways, but it is not a substitute for uh, low carbon resources. So again, it becomes very, very important, especially as you start looking going forward with some of the advanced nuclear I'll be talking about here in a little bit. I've just been focusing on electricity thus far, but there are other things, especially as like I said, that we could go in. EPRI has studied this of looking at some of the advanced nuclear that has some increased amounts of margin, has a smaller footprint, capable of being able to not only just as it has there in the orange where they're generating electricity, but also taking the steam and being able to use that directly to be able to go to a high temperature electrolyzer, produce hydrogen. It also is able to used in a distillation plant, be able to provide clean water. And people don't think of it, but the city of Lincoln has a district energy plant, and they basically have boilers that are providing all of the cooling for like the downtown state buildings and some of the university buildings. And they use the steam to basically through a steam chiller for cooling and also for steam for the heating. So again, if you start shrinking these nuclear islands down smaller and having a smaller footprint, you have the capability and ability to be able to go forward. And so that's why you're starting to hear so much about small modular reactors, about some of the advanced nuclear that's in there. So if we're looking at the future of going through there, we need to start off with, we have nuclear in the plant right now. Cooper's licensed to operate to 2034. We have been maintaining the plant over the time frame such that the extension to 2054 is very feasible. So we've already been investing in all the pumps have been replaced. The major transformers have all been replaced. So you go through over the years, we've been investing as we've been going, and based upon that replacement and upgrade, we have a very feasible path for an extension out to 2054. We did conduct an integrated resource plan looking at our long-range generation needs through 2050, and it recommended that we needed to look at Cooper for extending the license. We've done basically a feasibility study, and have gone through and looked at that, and we're planning on at the NPPD board meeting this week, we're going to be taking in asking the board for a final decision to be able to start going forward to work on the effort to be able to extend the license from 2034 to 2054. What we do when we extend the license is we're going through a lot of analysis. We're looking at that. We're looking at equipment, looking at trends, making sure we have aging management programs to be able to detect if there's any sort of wear. We do additional inspections. So this is all kind of ongoing. So we've already been doing that for the last 20 years. And what the feasibility study said is that we don't have any sort of major risks in that area. And so we'll be going forward looking at that. But that's just the equipment. We really have to also then look at the existing and future workforce. That's just as important, if not more important. The plant is good, but it's the people that really make it. And so we've established partnerships with local schools and colleges. We're able to develop and attract employee pipelines, support safe operation now and in the future. So, when you look at some of the advantages of Cooper Nuclear Station, especially in southeast Nebraska, we pump roughly about 600 million annually into the local economy down in this area. So again, there's a lot of very good jobs. We're working more and more with schools to attract people. We find that we really do very well with being able to have high talent that comes in from the state of Nebraska, be able to keep people here so we don't have to worry about brain drain, and they're having they don't have to leave the state to go on. We're finding that especially some of the younger workforce that really would like to stick around in here. And so we have those opportunities. We just want to be able to point that on out to them. As far as new technologies, we remain engaged going in the future. We're currently doing a siting study that's underway for small modular reactors. We're looking across the entire state. We had funding from the state to basically look at and come up with a selection of numbers. We're currently wrapping up phase one of that, which will identify roughly about 30 different locations across the state where we could look at putting one, and then the next phase we'll go in and do some detailed analysis, maybe some core drilling to be able to look at the actual soil and kind of take it a step further and then narrow that on down to about 4. And from there, we may even look at some advanced licensing and have something that's going in. Again, that's something that's coming on down just to be able to do this. If we decide that we wanted to build a new nuclear plant, and we knew that right now today, it would be 10 years before we would have it in place. So there's a very long lead time, and we'll be talking about some of these that are currently in progress. And there's over 20 different projects across North America that are currently engaged in wanting to have demonstration projects supposed to be coming online by the end of this decade, around about 2030. Based on that, we want to be able to make sure that we've gotten rid of the risks. The first of a kind, anytime you do a first of a kind, you will always you learn things and be able to see a reduction in price and be able to reduce the amount of risk that you have. And so that's why we stay engaged with all those, looking at that and going forward. NEI tracks this, and you can see across the state, all the states that are blue, those are states where the legislature has had some sort of or stakeholder interest in advanced reactors in the state of Nebraska. As I said, there was a legislative bill to go out and to basically earmark some federal dollars for siting studies that we're currently in progress of doing. We've also looked at several other items to be able to court and be able to bring more nuclear power that's in there. You see the blue dots across the state, those are actual demonstration projects that are going for various different advanced reactors. And you can see even going up there into up into Canada. Right now, the 3 that are over there by Ontario, they're probably going to be some of the earlier ones that will probably come on in. It's possible that there's the one out in down in Texas is a Dow Chemical. They're actually looking at a smaller footprints that they're able to actually use the steam for their chemical processing that it's in there. So talked about advanced nuclear deployment, but what are the features and why do they have that? Well, in the past, we had very large power plants like Cooper Nuclear Station. It was 800. Some of them are 1,100, 1,400 megawatt plants. And when you have that much energy that's in there, obviously that's a lot of stored energy. These are much smaller. They're less than 300 megawatts. Some of them are even down around about 5 megawatts. So what they have is since they don't have as much energy storage there, they have a lot more margin of, they don't need active components. We require electricity. We require pumps to be able to keep things cool, to be able to keep on maintaining all of our safety systems. We have redundancy upon redundancy to make sure that all that equipment will work. At a lot of these, they have what they call walkaway safety. So if a plant were to trip, you would have it be just like the fuel that's out on our spent fuel pad. It's all very passive. So air comes in, cools. It's all air cooled, and it's going out there. They were actually building the plant out in Utah. And it was basically they would have water there that was on site, but they were going to have no cooling for it. They were going to have no water source needing that, and they were able to maintain that with all of the safety margins. Some of the new designs could reuse some of the waste, so it would greatly reduce the amount of spent fuel requiring disposal and reusing some of the spent fuel. Again, they have a variety of different items. They have different temperature. When they start looking at molten salt reactors and other things, a much higher temperature with a much lower pressure. So again, the footprints are very, very small. So there's a zone that they call a emergency planning zone, and around Cooper and around the larger plants that we currently have, it's basically a 10-mile radius around the plant. What they're able to do is they've actually been able to demonstrate that they can get that shrunk down to just the owner-controlled area, and some, the new scale had it approved that theirs was roughly about 40 acres. Some of these plants are looking at making it down to just their reactor building. So again, able to drop it on down to a matter of meters versus having large amounts of area. They need much less water, so there isn't an impact. They're they're built and can be built modularly, so they can be more factory manufacturing. So all the components, rather than sent to the site and assembled here and fabricated here, they're actually fabricated in a factory. So again, looking at from the cost, shipped here and basically kind of put together. They have a variety of different sizes. They range from the microreactors of 1 to 20 megawatts that actually fit on a flatbed truck, mobile and deployable. If you remembered back on, there was a couple of dots that were up in Alaska. Those are some Department of Energy, or excuse me, Department of Defense facilities. They're actually looking at some uh, uh, Army bases that are up in Alaska. They're at the end. They have to truck all their fuel in. They're actually looking at some of these micro reactors to be able to power the entire site up. A lot of them are in the range between 20 to 300. Those are called small modular reactors. So you can see those. They're built in a modular fashion. In this particular one, you're seeing something that a bunch of different vessels that are in there. And so the idea is that you build a containment structure and you're able to then put in one and be able to expand it. So you can put in 2 plants, you can put in 4 plants, 6, 8, all the way up to 12. But again, it now becomes, you can build a facility that would store 12 of them. And then if you don't have that sort of load growth that you need right now, you'd be able to in the future add that on in. And then some of them are the full size we talked about, which are up to 1,000 plus. Some of those just came online over in Georgia. And again, those are pretty much just basically, they're using some advanced features. They're using a lot of passive design, but again, they're a much higher energy output. So, and there's types of advanced reactors. So currently all of the commercial reactors are either they're all water-cooled reactors at this particular time frame. So we use water, and either it's a pressurized water reactor or it's a boiling water reactor. But now what you're seeing there, you see the small ones. Again, these are some of the vendors. There's probably over 30 different vendors that are out there that are vying for the money. There's been a lot of investment in by the Department of Energy. They've been spending over 500 million dollars investing in just to be able to get these up. That allows to take a risks to be able to go out for first of a kind. So you see the NuScale there, the light water small modular reactors. That's a technology that comes on in. That's what was being put in and being built in Utah. They've decided not to carry that one forward. Weren't able to get enough customers for the ultimate electricity, and so they've backed away from that. But they're looking at other locations they can put that. And they're actually looking at some areas in Europe where the first of those may be going. High temperature gas reactors. So instead of using water to cool the core, they use basically helium that's going through there. Again, it's operating at atmospheric pressure. They have encapsulated fuel. It's constantly being refueled, so there is no time frames that you have to shut down for fuel. It's just running through there. That's, again, it's a non-water cooled, and what they would do is with 4 of their units, they would be able to come up with a 300 megawatt site. And they're basically mostly built underground. So they basically drill kind of a hole in the ground and it goes in there. So it's protected from any sort of tornadoes or storms or anything else. Again, looking at a much smaller footprint, not needing large amounts of water to be able to keep them cooled. Liquid metal reactors they're showing the Natrium reactors or TerraPower. That's the one that Bill Gates is doing out in Wyoming. They're actively looking at conversion of some coal sites in Wyoming. Several of the plants that's been going on. All of these are looking at coming on, like I said, around the 2029, 2030, 2031 timeframe. And then going all the way up to like the molten salt reactors. And here you can see that there are several of them that they're showing terrestrial, but there's several of them that are shown. And again, the idea of the molten salt is that you can, the amount of pressure for you to take and get a very high temperature water, when you think about it, your pressure, because it turns to steam, it causes the steam to go higher and higher. With molten salt, one of the reasons they're going with some of these is they're able to get a much higher temperature out of the core, but again, it's at a very low pressure. So there's nothing to There's no driving force for dispersions or anything else. So again, there's a variety of different items that are out there. We are currently, Nebraska Public Power is currently following all of these different items. We're staying engaged with the industry, with EPRI, with NEI, trying to make sure that we understand, the risks of going, when would it be, we need to see the demonstrations, be able to have them proven as they're going forward. But all of these different types of designs have been around since the 40s. So these are not like brand new, gee, we've never tried this, don't know if this is going to work. They've been around, they've been in very small amounts and been able to be proven very, very safely. You look at the US Navy as an example, with all the submarines that they have, they've had excellent safety history with them. Again, they're very small reactors, much smaller than what we've talked about. And with that, they've been able to use the passive designs that are in there. And with that, that's all that I have, unless there's questions.
Okay, we do have some questions. Let me get into the chat first. I think that you mentioned this, but one question is, do you think there is a future for small scale nuclear generation?
Very much so. Very much so. There are so when you look at the micro reactors, that's actually got an awful lot of interest. Their business model is very interesting. They've actually looked at the risks that you would have for a small modular reactor. They would be operating them remotely. They don't believe that they would need to have a large security force because there would not be that sort of threat. So that is a possibility. However, the current regulations don't say anything different about one or the other, and so there would have to be some work with the NRC, and the NRC is trying to look at this and trying to look at risk based on the risks, saying is there some things that we could be doing, and making sure, the NRC is tasked with making sure that we operate these safely, and that they can be operated safely, and very firm believer that yes, they can be operated safely.
Okay. We have a question here. I enjoyed the presentation. I wish more people were less emotional and more logical in regard to the use of nuclear power. We're going to need, I'm going to have to scroll down here. More power. We are going to need more power and reliable 24/7 power sources. Exploring and utilizing a diversity of power, excuse me, sources is a must. Well done. And I think we would all agree with that. You don't disappoint, Dan. You did a really great presentation.
Well, thank you. I'm just a spokesperson. There's a lot of people that were a lot smarter than me that made the diverse portfolio. So
yeah, that's great. Okay, we have a few more questions. Is the spent fuel ever used to preheat water before it passes through the main portion of the reactor?
no. Once we discharge the spent fuel, we do not use it again. It maintains temperature. We maintain cooling, like I said, in the spent fuel pool until we put it into the canisters. They are not currently being reutilized. We are looking at some opportunities with that, but again, that's a long ways down the line. So
okay.
And I don't mean to
Can you
interrupt,
describe
but
the state of the?
Oh, I'm sorry. I don't mean to interrupt, but do you mind if I launch the survey now before we go on with all the questions?
that's fine by me.
Okay. So
And while you're doing that, I might mention that we are in the process of planning a possible tour to the nuclear plant in Brownsville. So keep up with our Facebook page, and we'll post it on there. So that should be very interesting if we're able to do that. We're thinking maybe sometime in mid-March.
Yeah, and again, you and I have talked about that. We for the longest time we did not do a lot of justice. Our view of life was keep your head down, stay out of the news, and life is good.
Yeah.
We saw that that's an error, and what we need to do is, this is a public perception to issue, and we need to be able to invite. So we're trying to be very, very transparent. We welcome people to come in to be able to look at it. A lot of people want to look at and see, is it safe? And again, very firm believer, we would not be doing this if we didn't believe it was. However, it doesn't matter what we really think. We really, it's the public, because it is a public perception and public
Yeah,
decision.
yeah, that's great. Okay, can you describe the state of the 20 projects that are going on now? Are there any that involve actual commercial generation?
Yeah, there actually are several of them that do. So the ones up in Ontario that they're looking at doing, they're actually looking at building a total of 5 of them up in Ontario and having them operational starting in 2030, 2031, 2032. They're the one that we talked about out in Utah. They were actually building it. It was going to be commercial and it was going to be turned over to the public power entities that were out there. There were a lot of small public power utilities, and but again, the whole risk reward got to the point where they didn't have enough buyers to be able to go in there to be able to make the business case. X Energy is doing that. Also, the ones over in Wyoming, they're actually looking at doing that now. It's going to be several years before they're actually producing electricity and going in there. But again, they're in progress. They're coming online in around about 2030, and some of those will actually be generating electricities to do that and going commercial after that.
Great. Okay. Why has NPPD had such success with nuclear, but OPPD's experience is the opposite?
I really can't speak for OPPD, but I will say that you know, a lot of times it's a matter of um, timing. So you know, there were a series of instances. We are a little bit larger of a site than what Fort Calhoun was, and so therefore costs could be spread over a little bit more. Now that can become an advantage, it can become a disadvantage, and so a lot of it kind of depends on uh, what is going on. But I know that we still work, and you know, we share back and forth. I know OPPD is while they don't currently have a nuclear plant, they are not closed to that. They're still looking at it and actively, you know, they help participate in the Advanced Nuclear Coalition. Um, you know, they help sponsor that activity that we have in Advanced Nuclear Forum. We've had that a couple different times in Nebraska. It was kind of a groundbreaking event that was in here. They're participating in it. They're kind of in the same stage that we are. You know, we happen to have an existing nuclear plant, so we're able to maintain that. Um, we would not be jumping into the small modular reactors just because of some unknown risks, and that's kind of where OPPD is also, I believe. And they're trying to monitor that. They're trying to look at what is the best options as they go forward. But they're certainly a very capable company, and they would certainly be able to do that if they choose to do that.
Okay. How is the heat from a small modular reactor converted to steam? Is the PWR cycle used, BWR or other?
So it depends upon the kind of plant that you have. So if it's the water cooled small modular reactors, it would be typically like a PWR type system. If it is a high temperature gas, where you saw that loop where we had the pressurized water, instead of pressurized water, what they're actually using gas to go take that circulating through and going over to a steam generator. If they're looking at molten salt as an example, it would be basically molten salt that was going through there. So they would typically use some sort of interchange of going through the core, be able to pick the heat up, take the heat out to a steam generator that would generate steam, and then that would basically produce their electricity.
Okay. How cost effective is nuclear for electricity generation?
So nuclear does have a very high fixed cost. You know, we have roughly about 660 people that work here on site, and plus a bunch of people that support up here out of Columbus. So again, it's a very labor intensive to be able to operate the plant safely. So that does tend to drive the costs up. However, they do operate 24/7, and so they're able to share some of those costs and be able to keep the overall costs down. The problem that you have is with that high fixed cost is if you're shutting them down all the time, they're not if they're not highly reliable, then then they become very, very expensive because you have to pay those same amount of costs whether you don't produce any megawatts or whether you're producing full amounts of megawatts. We have worked very, very hard in investing into the plant to make sure that it not only operates safely, but it's also maintained reliably. And so it's been able to operate through the things like like I said, the winter storm, Uri, the flood, the 2019 flood. We were at a flood stage for over 270 days, and it continued to operate 100% power safely during that entire time.
Yeah. Okay, can NPPD's nuclear life be extended?
Yes, it can. Right now, there are several plants that have extended the plants out from 60 years out to 80 years, and that's currently what we're going to be looking at. That's we've done the feasibility study. We have actually looked at that, and we do not see any sort of risks. And we are taking a proposal to our board this Thursday, asking them to authorize us to go ahead and start the engineering work to be able to look at a subsequent license renewal. We do all that analysis. That'll take us about 2 years, and we'll do a submittal. Take about 2 years for the NRC to go through. So we'd be looking at making our submittal in 2026, and then be able to have approval in 2028. And then that'd give us time to be able to actually implement it so that we'd be able to go. And so when 2034 comes, we'll just continue to operate to 2054. There is also an effort that's looking from EPRI that's looking and saying, even at 80 years, it's not necessarily a limit. They're looking at the way the plants are being maintained. They're starting to look at, is it possible that they'd be able to operate even for 100 years? It doesn't mean that you have a 100-year-old plant there. I mean, like the control systems are all brand new. It's not like you have this old Model T that's coming on down. You got to think of it as over the years we've been replacing different items. We've been putting in the new stereo. We've been putting in all the equipment in there and all the upgrades as it's been going. So.
Okay, why doesn't Nebraska have nuclear on the western side of the state to be able to distribute power into either the eastern or western national grids?
So we are looking at the siting study. We're looking across the entire state, and so that includes the panhandle and the western side. And again, we kind of broke the way that we did this is we kind of broke the state up into regions, and we're making sure that we have areas identified where you would potentially be able to do that. So like 30 different sites that we'd be able to look at that, and then based upon that, study that a little bit more to be able to narrow that down to say what is the best place as far as going. Part of that we have to look at where is the transmission lines, where we currently have those, because we have to be able to get the energy on over there. And so we would certainly, that'd be one of the factors of looking at where the existing infrastructure is, being able to site some plants at that particular location.
Okay. Now, I think this is the last question. There's some more in the chat, but about costs, recent studies suggest nuclear costs about the same as wind, and both are a little more expensive than gas. Coal and solar are more expensive.
Nuclear is more expensive, depending upon how you're actually measuring it. It can be right on par with wind. So we look at it in two different ways, and we look at the fixed cost. You have a certain fixed cost for wind, and you have a certain fixed cost for nuclear. The fixed cost for wind, as they're going through to be able to build to the scale that you have of Cooper, is probably roughly about the same. Their variable cost, though, is very, very cheap. I mean, the wind is free. So they have no fuel costs. We have some fuel costs, but again, our fuel costs are very, very low. So we have a very variable cost. We get dispatched into the market also. But compared to, for example, Gerald Gentleman, our coal plant that's out in North Platte, that also is able to cycle up and down and go through, they are a very low cost power provider. And so it's that symbiotic relationship between the two. We're able to do a base load, be able to maintain, keep our carbon emissions down, but we're also able to keep our prices on down, and that which is driving overall costs for the state of Nebraska to being the 5th lowest.
Okay, we've got a few comments here. Will SMRs help reduce the threat demand on the grid? If you can place small reactors in multiple locations, it seems like communities, brownfields could have reliable power that don't require miles of transmission lines and multiple substations.
That's really kind of the working model for the microreactors for the Oklo reactor as an example. They want to be able to plant these into remote locations, be able to put them and power up almost in a microgrid type fashion. Just a small little grid. They'll be interconnected, but provide the power that's right there without having to do all of the transmission. Their working model, the way that they would do that is most of these would be operated from some sort of central location, and they would be doing a lot of remote monitoring going back and forth. The NRC's regulations right now would not allow that, but they are looking at that and looking at the risks that that would pose and saying, okay, for them to be able to have that, what's the worst thing that could happen? Is there any way that they could get any sort of release of radiation? Or all of that's being worked at as they're going forward. But again, that's one of the promises of the microreactors. That's one of the reasons why the Department of Defense is looking at putting them up in Alaska. It's a more reliable power source for them. It'll always be there. They don't have to constantly refuel it. They already have a security force there to be able to monitor it. They would be monitoring it locally, but to take this out to across the United States into the civilian, there's going to have to be some changes that would, that would have to be studied by the NRC and have to be approved by the NRC before we'd be able to do that.
Okay, we have just a couple more comments. We live 3 miles from Turkey Point in Miami. The many times I had to drive South Dixie Highway with no electric power. On the news, they said there was a slight release of radioactivity, but not enough to make anyone sick. I credit Turkey Point with me losing my health at a very young age. Please, no more nuclear power in Nebraska. Do you have a comment for that, or?
As I said, I'm a very firm believer in nuclear power, but it is a public policy decision as we go forward. I don't know any of the incidents, and I could not even speak on any of the incidents that she's talking about from Turkey Point down in Florida. That is very unfortunate. I would not see. I do know that there has never been a release beyond release from the plants as they've been going. It's very strictly monitored. There are the NRC has 2 individuals always on site here that is always constantly monitoring, making sure that we're maintaining and operating the plant safely, and that we are always taking safety as the utmost, which is what we do. Turkey Point is typically has always been a well-ran plant as far as I know, but I couldn't speak to anything specifically that she was in there. And I'm sorry she has that opinion, but I would be happy to continue in any sort of discussions, and if there was any questions or anything else. But again, that she has that. You said it was a she. I keep referring to a she.
Yes, I think so.
Okay. I just want to make sure I wasn't offending somebody when I was doing that, but
no, yeah.
So I mean, that's the whole issue. It is a public policy decision. I obviously have an opinion. I've been engaged into that. I would strongly recommend reaching out and trying to look at other information, and I hope that she's able to get answers. I'd be happy to point her towards resources if she wanted to, but
okay, thank you. Okay, there's one more comment here. The OPPD plant was the smallest nuclear plant in the country, and the floods didn't help. So that was obviously just a comment, but I don't see any more questions. Let me just double check here. Yeah. One more question and then we'll be done.
okay.
You mentioned a citing study some 30 possible locations. Is that publicity available for review? You
Uh,
mentioned the sittings.
Oh, go ahead.
No, I think it's siting study. Okay. Yeah.
Yeah, yes, we do have a siting study. The results have not been released as of yet. We are currently finalizing that. We'll be working with the state. The state is actually the one we're conducting it for the state, but we're looking at being able to release that as soon as phase one is completed. We will be getting that out, and you'll be seeing that will be coming out. And again, it's looking at locations, and it's not saying we're going to plan on building or anything that's in there. It's just looking at potential locations and saying, you know, once you have them identified, now comes the really tough part. You know, you have to start looking at and getting engagement from the communities that are around that and saying, is this something that you want or don't you want? You know, and we have to be able to engage that dialogue and be able to do that. And that's where we would start taking and going from this down to a smaller subset, and eventually getting to the point, again, using community engagement, because it's consent based, to make sure that
Yeah.
we're all on the same page, and we would sit there and look at the potential of something beyond for the next nuclear plant in Nebraska.
Okay, well, Dan, thank you very much. We can't really thank you enough for sharing your time and expertise on this topic. And I would encourage everybody to follow Conservation Nebraska's Facebook page to find out about upcoming events, including the Cooper plant tour. So everyone have a nice evening, and thank you again, Dan.
You bet. Thank you so much for the opportunity. I really appreciate it. Thank you.
Really enjoyed it. Okay, bye-bye.
Bye.